Today I will give a presentation on protection of HVDC systems, which is part of the deliverables 3.4 of the InnoDC project. On protection of hybrid AC and DC grid, feasible and implementable approaches. The main research contents have been summarized as a paper, which has been accepted by IEEE transactions on industrial electronics. The paper mainly focuses on doing the research on the warp-side AC fault, which is one of the most severe faults in MMC-based HVDC systems. So two strategies has been proposed to protect the full bridge MMC converters during this kind of fault. The contents of the presentations are listed here. First, I will give some introductions on the research background. Nowadays, normally there are two kinds of HVDC technologies. The first one is the LCC-based technology. The second one is the VSC-based technology. Both these two technologies have their own advantages and disadvantages. But with the development of the renewable energy nowadays, the VSC-based HVDC technology has been developing very fast, but there are still some challenges for this kind of technology, like the DC fault isolation and the high power losses. Regarding the fault for HVDC systems, normally there will be some AC side faults and DC side faults and even some components faults, like the device faults and the cooling system faults. But this research is mainly focused on the warp-side AC faults. A bipolar HVDC system is given here. Normally, a bipolar HVDC system will contain positive bars and negative DC bars, and the converter are connected to the AC grid with the interface transformer. A detailed configurations of the HVDC MMC-based HVDC systems are given here. This is the MMC converters, and this is the interface transformers. The converter are connected with the AC grid through a interface transformer. A warp-side is the kind of fault normally happens between the interface transformer and the converter. And the reason of the warp-side fault can be the bushing insulation failures, like the figure shows here. If there is a insulation failure here, there will be some warp-side faults. I will give some analysis on the phenomena of the warp-side fault in MMC-based HVDC systems. Normally, in bipolar HVDC systems, the output of the voltage will have a DC offside, which means all the voltage is beyond the zero potential. But after the fault, after a warp-side AC fault, the DC offside will disappear, which means the AC side output voltage will contain the negative cycles. This phenomenon will cause severe consequence to the MMC converter. One of the consequences is that if there is a fault happens at the warp side, it will create a zero sequence path for the MMC converter. It will evolve in a very large zero sequence current, which will cause the MMC converter to be blocked. But after the MMC converter being blocked, the DC bars will charge the capacitor in the upper arm of the sub-modules. And in the most severe conditions, the sub-module voltage can be charged to be 2 per unit, which is a very severe consequence for the MMC converter. In order to show the consequence, we do a simulation in PSCAD. Once there is a single phase to the ground fault happens at the valve side of the MMC converter. From the simulation results, we can see that the upper arm, the submodule in the upper arm has been charged to 2 per unit. It means there will be a severe overvoltage if the fault happens. Then in order to avoid this kind of overvoltage, some protection approaches has been proposed. Possible solutions. Normally there are two kinds of possible solutions to trying to protect the valve side AC fault. One is disconnect the AC side connections. The other is disconnect the DC side connections. But for the first solution, there's a problem in that the action of the AC circuit breaker is too slow. It cannot protect the MMC converter in time during the valve side fault. And the other solution, if we install a DC circuit breaker in the DC side, sometimes it can protect the MMC converter from this kind of fault, but this solution is of high cost. So we proposed methods which aims to reduce the DC side voltage directly. This is the detailed configurations of the proposed methods. We install a Thyristor branch at the terminal of the MMC converter. Once the valve side fault happens here, we just trigger the Thyristor branch to reduce the DC side voltage directly. In this way, we can avoid the some modules in the MMC converters to be overcharged. In order to protect the MMC converter from the valve side fault, first we need to detect the fault. Then we propose the methods. Due to that, the fault phenomena at the valve side and the grid side is totally different. We proposed a method which is we use zero sequence current to detect the valve side fault, because if a fault happens at the grid side, there will be no zero sequence current flowing from the converter. So we can use the zero sequence current to detect the valve side fault. It means if the magnitude of the zero sequence current is higher than a threshold, so we consider a fault happened at the valve side. We do a simulation to verify the proposed methods. With the proposed methods, if a valve side fault is detected, we trigger the Thyristor branch, then we block the converter. From the simulation results, we can see that with the proposed methods, there will be no some module over voltage happens here. This means the proposed methods can protect the MMC converter. If the Thyristor branch is triggered to protect the faulted converter, it will also cause another consequence, is that it will cause a short circuit of the DC grid, which is also a fault for the whole DC grid. But a good direction is that the full bridge MMC converters can control the DC side current. If a DC side fault is detected, it is very easy to control the output current of the converter to be zero. Then the remote converter can work as a StatCom. So we proposed a control loop to avoid the overcurrent in the DC side when the Thyristor branch is triggered. We also proposed an active protection method, which means if a fault happens here, we keep the full bridge MMC converters to be active, other than being blocked directly. In this way, we can go further to detect whether the fault here is a permanent fault or a non-permanent fault. If it is a permanent fault, we do the same way to block the converter and switch off the ACCBs. But if the fault here is a non-permanent fault, we will just rebuild the DC side voltage and rebuild the AC side voltage to make the whole system recover quickly. But this is the control diagrams we proposed for the active protection methods. We add another zero sequence current controller here to make the converter can be kept to be active during the fault. And we also propose a method which is we inject a zero sequence component after the fault to detect whether the fault has been cleared or not. This is a flow chart of the proposed active protection strategy. First, we detect if the fault happens, and if the fault happens, we will trigger the Thyristor branch, but we keep the full bridge MMC converter to be active. We use the DC side control and AC side control methods to keep the MMC converter to be active. In this way, we have the opportunity to inject a zero sequence current components to detect whether the fault has been cleared or not. If it is a permanent fault, we will block the MMC converter and switch off the ACCBs. And if it is a non-permanent fault, we will rebuild the DC and AC side voltage and make the system to recover. We do some more simulations to verify the proposed methods. We built a 2-terminal and also a 3-terminal system in PSCAD. The parameters of the systems are listed here. First, we do a simulation with the traditional protection methods, which means that we block the MMC converter after the fault is detected. From the simulation results, we can see that after the fault, if we block the full bridge MMC converter directly, there will be a severe overcurrent in the upper arms of some modules. Then we do a simulation with our proposed protection methods. If the fault is detected, we first trigger the Thyristor branch, then we block the MMC converter. After that, we switch off the AC side circuit breakers. And from the simulation results shown here, we can see that there will be no overvoltage happens with the proposed methods. We also do a simulation to verify the active protection methods we proposed, which means during the fault we trigger the Thyristor and we keep the control the MMC converters, make the converter to be active. From the simulation results, we can see that there is no overvoltage and no overcurrent happens with the proposed methods. If the full bridge MMC converter are kept to be active, we have the opportunity, have the chance to inject a zero sequence component to detect the types of the fault. If we still can detect the zero sequence components, the zero sequence current, it means the faults are still there. Then we consider the fault as a permanent fault. We will block the converter and switch off the ACCBs. But if we cannot detect the zero sequence current, it means the fault has been cleared. In this way, we can rebuild the AC side voltage and the DC side voltage of the MMC converter, and the whole HVDC systems can be recovered. We also do a simulation to verify the proposed methods in a 2-phase and in a 3-phase fault to see whether the methods can protect the converter under the 2-phase and 3-phase fault. From the simulation results, we can see that the proposed methods can protect the MMC converters under the 2-phase and 3-phase fault. There's no overcurrent and over voltage happens. But if we use a traditional protection methods, it means from the simulation results we can see that under the 2-phase and under the 3-phase fault, there will be severe over voltage happens. We do a simulation on multi-terminal systems to see how much influence of the proposed methods have on the total multi-terminal systems. And if a fault happens here, we use our proposed protection method to isolate the fault. After the fault is isolated, and then the whole system can be recovered. The simulation results show that after the fault is isolated, the whole multi-terminal systems can be recovered in a short time. In order to show the advantages of the proposed methods, we also do some comparisons with other possible solutions. The first one is the DCCB-based approach. We install DC side circuit breakers to protect the valve side fault, to trying to make the MMC converters to avoid being overcharged. From the simulation results, we can see that even with the DCCB, the sum module still has been overcharged because the operation of the DCCB normally needs 2 or 3 milliseconds within this period of time, so some modules will be overcharged. But with the proposed methods, since the Thyristor branch can operate faster than the DCCB, the protection performance is much better than using a DCCB. Another proposed protection methods by other researchers is called the zero voltage protection methods, which means they use the full bridge MMC converters to reduce the DC side voltage to be zero directly after the fault. In this way, the severe over voltage problem can be avoided for full bridge MMC converters. But this method contains a high risk in that sometimes if a large disturbance are injected to the systems, there will be some overcurrent happens for the MMC converters. And if the overcurrent occurs and causing the full bridge MMC converters being blocked, so the methods will lose the target, lose the capability to protect the MMC converters from overvoltage. But in our proposed methods, we trigger the Thyristor branch, so most of the energy will go through the Thyristor branch, not inject into the MMC converters. So in this way, the proposed methods can work better than the zero voltage methods. Then comes to the conclusion. In the whole research, the theoretical analysis on the valve side AC fault has been done, and the 2 protection approaches has been proposed in order to protect the full bridge MMC converters from being overcharged, and in order to make the whole system to be recovered quickly, an active protection methods also be proposed. The effectiveness of the proposed methods has been verified in PSCAD with both a point-to-point link and also a multi-terminal systems. And to show the advantages of the proposed methods, it has been compared with some other possible solutions. In conclusion, so the proposed methods in this paper, in this research, is a cost-effective and effective solutions to protect the full bridge MMC converters from being overcharged once a valve side fault happens.